Alright, so let's do a conservation of momentum problem. And the basic idea, all these are pretty much the same. Let's say that this is ice. This is an ice surface, and there's, let's say, a child standing on the ice and holding her hands out. I can't draw very well. And let's say there's a parent, a mother, let's say, holding the child. They're getting ready to push off of each other. Okay, so they're standing on ice. The mother pushes off. So this is the mother. So we'll say we want to know the mass of the mother, and we want to know the mass of the child. And when the mother pushes off, the mother goes in this direction. When the child pushes off, the child goes in this direction. And the mother will go with a velocity, we'll call it the velocity of the mother. And the child will go with a velocity, we'll call it the velocity of the child. Now notice one thing that's important. One of these is they're both going in the opposite direction. So the general thing that we tend to do is whatever direction is the positive x direction, and of course in this case it's the velocity of the mother, that'll end up being the positive velocity. The other one will have to be a negative velocity, but it'll come out in the equation when we do it, so the negative only just indicates that that's the velocities in this direction are negative velocities. Okay. All right. And so let's get started. So the basic idea of the conservation of momentum is the momentum before something, some interaction. So these two are pushing off of each other, right? The mother and the child are pushing off of each other, but before they push off of each other, they're at rest with respect to each other. So remember, momentum is the value of momentum, p, is mass times velocity. So without any velocity, the momentum is zero. And so before they push off of each other, the total momentum is zero. And then after they push off, there's going to be some sum of the momentum of the mother plus the momentum of the child. So the way we write sum in mathematics is using the sigma. So we have to add up the momentum of everything after, and that is after the push. And so that's actually pretty simple to do, since we've already defined some of the variables. So we have the mass of the mother times the velocity of the mother, and we have plus, and I'll get back to that plus in just a second, the mass of the child times the velocity of the child. And let's say that let's say, just for the sake of argument, that the weight of the mother is, I don't know, let's say 550 newtons, and the mass of the child, let's say we already know that the mass of the child is, I don't know, how about 25 kilograms. Now notice I gave you the weight of the mother, but of course, if you know the weight from weight is equal to mass times little g, then of course the mass of the mother is equal to the weight of the mother divided by little g. All right, and so let's put the numbers in. So that's 550 newtons divided by 9.8 meters per second squared. And so now we're going to get the mass of the mother. So let's see, 550 divided by 9.8 gives us 56.12, or so I'm just going to say 56.1. Alright, so here's when we round, we get 56.1 kilograms. Oops, I forgot the G for the mass of the child. And let's say that we measured, someone who was like over here and measured the velocity of the mother, and we want to know from the conservation of momentum, this is the conservation of momentum, we want to know what's the velocity of the child, right? So we have an equation, and we can actually just take this equation and solve for the velocity of the child, right? And so I'm going to rewrite that. Oh, I got to give you the velocity of the mother. So I'm just going to do it in the proper units. The velocity of the mother is measured to be, I don't know, how about 2 meters per second, just to make things simple. So that's the velocity of the mother, and we're going to take this equation, okay, so from above, this equation, 0 is equal to the mass of the mother times the velocity of the mother plus the mass of the child times the velocity of the child. And we have to solve this for the velocity of the child. Well, these are separated, these two parts, the mass of the mother times velocity of the mother, that's what we call a term, since it's separated by a plus sign. So to get rid of that, or not to get rid of it, but to isolate the velocity of the child, we have to put this term on the other side. And so all we're going to have to do is add a negative mass of the mother, the velocity of the mother, to both sides of the equation. Okay, so here we go. Negative mass of the mother times velocity of the mother. So that's going to be kind of like added to 0 is equal to, positive mass of the mother times velocity of the mother. And then, of course, since we subtract mass of the mother times velocity of the mother. You don't normally do this step because that, of course, adds up to 0, and then we still have plus the mass of the child times the velocity of the child. Okay, so kind of the last step. Remember, this is 0. These two combined equals 0. Okay, so it's really now we just have to solve for the velocity of the child. So the velocity of the child is equal to negative the mass of the, so it's the mass of the mother times velocity of the mother, and all I'm doing is dividing both sides by the mass of the child. So there we go, divided by the mass of the child. And we have all that information. Now we can put all that in. Notice we get a negative velocity of the child, which should make sense, right? Because, the child's moving in the opposite direction. So let's see, it's the mass of the child was 25, the mass of the mother was 56.1. So I've forgotten those already. Let's see, so it's going to be 56.1 kilograms. Kilograms times the velocity of the mother, which is 2 meters per second, and then that's all divided by 25 kilograms. Right, and the kilograms cancel, of course, leaving you an answer in meters per second. All right, so let's do a. So when we put the numbers in, I get a negative. Make sure that negative 4.5 meters per second. Meters per second. Sorry, I was running out of room there. Negative 4.5. That's a 5 meters per second. So when you round it, it's about negative 4.5. All right. So there's an example with conservation of momentum.